Hi there guys, welcome to this video. Really excited about this video because we're going to be taking a look at a problem from a sixth term examination paper. So those of you that are doing A-level maths or A-level further maths in the UK may be familiar with the STEP papers, which typically if you're wanting to go to university to do undergraduate studies in mathematics, particularly at a high-ranking university, it is very common for you to have to achieve a particular grade, a particular level in a STEP paper. So the problem that I've chosen is from the Step 3 paper from 2022, and it's problem number 5 or question number 5 from that paper. So the purpose of this video really is not just to give you a model solution to this problem. You can find a model solution. There's mark schemes, and I'm sure that there's other videos that you can watch on YouTube where people will give model solutions and things like that. It's not really the specific problem or even the specific solution to this specific problem that is the focus of this video. It's more, in a lot of cases, how did that solution come about? What kind of things did I notice? The solution is my solution. So unless I actually explicitly say in these videos where I solve problems in mathematics, unless I specifically say so, then I haven't looked at a model solution to that problem. Any solutions that I give are my solutions. They may contain mistakes, therefore, which I might not know about unless somebody tells me about them. But generally speaking, I've checked through my solutions and I'm satisfied that it's correct, but the solutions are mine. And the whole point of these videos is that I articulate as well as I can, the process by which I arrived at my solution. Because I think if I just give a model solution, I just say, do this, do this, do this, and you get the answer. Sometimes unusual steps happen in solutions to non-routine problems. And one of the difficulties that you might have as a learner of mathematics is understanding what motivates those steps. How does that person know to do that thing? And sometimes the answer to that is that person did not really know to do that thing, or didn't expect to have to do that thing, or didn't even know that that thing was actually going to work. And yet there was still something that motivated it, and it's that kind of process. There's a few steps that I've taken in this where that's happened, where I've done something, I've not necessarily had a clear idea about what I want to do, and I've done something and it's kind of stimulated some kind of idea, which when I've actually committed myself then to that idea and followed through with it, it's actually led me to a suitable solution to the problem. So just to give you a bit of background into who I am a private maths tutor, and I specialize in providing tuition for people who are looking for GCSE higher, IGCSE A-level maths, A-level further maths, particularly people that are looking to go on to elite academic institutions to study mathematics or mathematically related subjects such as physics or computer science, data science, things like this, at maybe Oxford, Cambridge, Warwick, Durham, and so on and so forth. This is why I'm concentrating on STEP in this video, because STEP is a big part of the university application process for mathematics, and it's something that I'm quite involved with. I have been involved with in the past. And if you are doing STEP, or if you're doing the MAT in November later this year, if you do want some help with that, please get in touch, and I'd love to have a discussion with you about how I can help you, what your needs are, what your requirements are, and how we can move forward, and how we can prepare you, how I can prepare you for your STEP or your MAT exams or your normal A-level maths exams. I'd love to hear from you and I'd love to have a discussion with you. Okay, so let's have a look at the problem. So I'm going to put a link to this paper in the description to this video. So it's problem number 5. And what we need to show, there's several parts to this. And the first part is we need to show that the integral from minus a to a of 1 over 1 plus e to the power of x dx is equal to a, and for all a greater than or equal to 0. For all a greater than or equal to 0. So if it looks like I'm looking down here, that's because I am, because that's where I've got the problem up on my computer screen. Okay, so this is the first part to this is fairly routine. However, there were some tricky bits to this. First of all, you've got to decide how are you going to integrate this. So you've got to be familiar with the typical techniques for integration at A level. So you've got things like integration by parts, integration by substitution. You may have come across things like reduction formulae at some point if you do further maths. That's always a possibility using reduction formulae. But here I was immediately drawn to the idea of using integration by substitution. So the next problem that you've got, if that's what you decide to do, and that is what I decided to do, which substitution do you use? There might be several possibilities, but you've got to decide on one. Now, usually, the substitution that you need to make is fairly obvious, but not always. But in this case, it turns out to be quite obvious. So, by the way, I'm just going to call this I, just so that I don't have to keep writing this out all the time. So the substitution that I'm going to make is u equals e to the power of x. Okay? It is possible to do this using the substitution u equals 1 plus e to the power of x as well. It really doesn't make too much difference. But I'm going to use u equals e to the power of x. And there might be other possibilities, though, why you would choose something other than this one or 1 plus e to the power of x. You'd have to really have a good reason to do so, because it'd make it, in my opinion, more complicated than it needs to be. So, okay, I need to change all of this into an integral in u. Okay, so this is an integral in x. I need to change it all now to an integral in u. So that means that I need to sort out this bit, the integrand. I need to sort out the dx, and I need to sort out also these limits. So I do these one step at a time. So first thing is I deal with the integrand. Typically, you want to replace, you want to get the integrand completely in terms of u. Although, if you've got a little bit of foresight, in some cases, it might not be necessary to do that. Sometimes you might be able to leave some part of the integrand in terms of x, and it might actually cancel out at some point when you start to mess around with this thing. But typically what you're trying to do is get the integrand completely in terms of u. So what do we get? We get 1 over 1 plus u. Okay, so how do I get rid of the dx? I differentiate my substitution, and I get e to the x, which of course is equal to u. And that means, therefore, that dx, we do a naughty step here, I guess. We multiply through by dx, divide through by u. We get something like 1 over u du. Okay, understand that what we do here when we do this is just a formal symbolic manipulation. Generally speaking, this is not a fraction. Du by dx is not a fraction. Du is not the numerator. Dx is not the denominator. It's effectively a single thing. But for various reasons, which I'm not going to get into in this video, this formal manipulation gets us to the end point that we need to get to. So this is kind of a meaningless thing to us at this stage in many ways. It's just something that allows us to get to where we need to be. Okay, so I replaced the dx with 1 over u du. By the way, I'm thinking about this here as a multiplication effectively. 1 over u times du. When x is equal to a, u is going to be equal to e to the a. Similarly, when x is equal to minus a, I get e to the minus a. So I've got an integral now, which I can tidy up to give e to the minus a, e to the a. 1 over u times u plus 1, or 1 plus u, whatever, du. Okay, so if you're familiar again with the kinds of techniques that you need to use when it comes to doing integration, you'll recognize that you need to use partial fractions for this. So 1 over u times u plus 1 is equal to, it's going to be a over u plus b over u plus 1. What we'll find is that a is equal to 1, I want to say, and b is going to be equal to minus 1. So this will be equal to 1 over u minus 1 over u plus 1. I'm just trying to recall I've got my notes here, but I'm just trying to recall what I did get. So we get e to the minus a, e to the a, over, of the integral of 1 over u minus 1 over u plus 1 du. Okay, now everything's straightforward. This is equal to natural logarithm of, okay, strictly speaking, it will be modulus of u, but we can see that u is going to be greater than or equal to 0, well, greater than 0, it's exponential. Greater than 0 anyway, so it's going to be positive. So I'm not going to worry too much about the modulus signs here. So it's going to be natural logarithm of u minus the natural logarithm of u plus 1 between e to the minus a and e to the a. At this point, actually, I was starting to get a little bit worried that I'd maybe done something wrong, because what I'm wanting is that my integral is equal to a. And I saw the natural logarithms come up, and particularly this u plus 1 here, and I was starting to get a little bit uncertain. But I followed through, carried on, and as we'll see, everything turns out okay in the end. So what do we get here? We get natural logarithm of e to the a. Okay, so that's just going to be a minus the natural logarithm of e to the a plus, or 1 plus e to the a minus, and it's going to be natural logarithm of e to the minus a, which is going to be minus a, minus the natural logarithm of 1 plus e to the minus a. Okay, which is going to be 2a plus the natural logarithm of, and I'm not going to go into I'm not going to spell out all of the details of what I'm doing here, but I'm just using laws of logarithms. So I get 2a plus natural logarithm of 1 plus e to the minus a over 1 plus e to the a. Again, at this point, I was starting to think, oh, something's not quite right here. I should be getting something like that, but everything works out in the end. Sometimes you've got to have a little bit of faith, you've got to have a bit of perseverance, you've got to be prepared to see what happens when you try various things out. So when presented with something like this, the only thing that I could really think to do was just to take this to one side, this 1 plus e to the minus a over 1 plus e to the a, and I multiplied numerator and denominator of this by e to the a. And that gives me e to the a plus 1 over e to the a times 1 plus e to the a. Well, that then cancels with that, so we get a common factor in the numerator and denominator, and I just get e to the minus a. Aha, okay, so this is going to be equal to 2a plus the natural logarithm of e to the minus a, which of course is 2a minus a, which is just equal to A, which is exactly what I needed. Okay, so it really does pay sometimes to have a bit of faith in what you've done. Admittedly, I got to this stage originally and I really thought I'd done something wrong. There's no problem if you want to check. If you feel that you've done something wrong, I urge you to check, because it will be better for you to pick up on any mistakes that you've made it earlier, sooner rather than later, when it's potentially going to be more difficult for you to rectify the problem. So if you do have a feeling that you've done something wrong, just have a bit of a check. But if you can't see that you've done anything wrong, in a lot of cases, just maybe accept that you've done everything right. Obviously, we're not infallible. We can make mistakes, but there does come a point where your confidence in what you're doing is great enough for you to be able to judge, yes, this is correct, or no, this is incorrect, and be able to do that with a high degree of accuracy. So I did double check at this stage. I went through, I found that everything was to my satisfaction, at least. So I thought, well, okay, that means that I'm going to have to do something with this. And it didn't take me long to figure out what I needed to do. So that's the first part of the problem. So now let's have a look at part 2. Okay, so let's move on to part 2 of this problem. By the way, guys, this is a fairly new YouTube channel. At the time of recording this video, I've only got a few subscribers, so I'd really appreciate it if you would hit that subscribe button and let other people know about this video. There's going to be a lot more STEP and MAT content going up on this video, on this channel, which hopefully you'll find interesting and useful. Hit the like button, leave a comment in the comment section. I'll be really grateful for that. Okay, so part 2 of this, and I'll just read out the problem. You can, again, I'll leave a link to this paper in the description to this video so you can see the problem for yourself. Part 2 says, explain why, if g is a continuous function and the integral from 0 to a of g of x dx equals 0 for all a greater than or equal to 0, for all a greater than or equal to 0, then g of x equals 0 for all x greater than or equal to 0. Okay, so this is it. Even though as part of your A-level maths, the notion of continuous function is, it's not given a lot of emphasis. Most of the functions that you do come across at A-level are continuous functions, and that means that you can kind of bypass a lot of certain difficulties that arise when you deal with more general types of functions. There are some discontinuous functions potentially that you come across, but it's done in kind of an inconspicuous sort of way. So you are expected to have kind of an intuitive idea of what is meant by a continuous function. You don't need to know what it means. There is a precise definition of, all sorts of precise definitions of continuous function within mathematics, and it's not, and there's different types of continuity as well, but the notion of continuous function can be formulated in a very precise way. One common way is the so-called epsilon delta definition, which is very, very common, very widely used. And if you go to university to do mathematics, you'll almost certainly encounter this. You don't need to know that. Okay, I'm not saying that. What I mean is you don't need to know that in order to kind of answer this question. You can do it in more of an intuitive sort of way. That's not me saying that you don't need to know what is meant by a continuous function in a precise sense, or that you shouldn't bother learning about it. If you want to, I do encourage you to have a look at that, because it is interesting how this notion of continuity can be captured in a very precise sense, although it does lead to certain difficulties, certain functions that, although continuous, have very pathological behaviors, which we're not going to worry about too much here. So why is it, if g is a continuous function, so the understanding of continuous function that we're going to take is a much more intuitive sense, which is something along the lines of a continuous function is one whose graph can be drawn without taking your pen off the page, and that will suffice for us. Okay, that's going to suffice for us at this stage. Anybody that's watching this that has done undergraduate maths or any kind of real analysis where you've dealt with epsilon delta definitions will know that the definition that I've just stated, the intuitive definition, is far from acceptable at a higher level, but it's going to be acceptable for what we need to do. So the idea is that if we think about the graph of our function, if the function was, let's say, above the x-axis at some point, and this might be really, really heavily zoomed in on the function. So this is not this could be a very small region of the plane that we're looking at here. If there is a point, if our function takes a positive value here, then there's no way, without taking my pen off the page, that I could get back down to the x-axis or below the x-axis or something like that. There's no way that I could get from here to here without taking my pen off the page if this is a continuous function. So in other words, if I know that the function is non-zero here and 0 here, then it must also be non-zero for the values, for some of the values in between this value and this value. And similarly over the other side. Okay, I don't know what the function looks like. It might be quite wiggly or whatever, but there's going to be some region where the function is some definite area, some non-zero area, where the function is going to take non-zero values. Okay, so the integral here of this function, even if the function was 0 for all of the rest of these values here, this would give a positive area. This would have a positive area, or non-zero area, maybe I should say, a non-zero area, and therefore the integral of this function between these two values here, so we've got a and b, the integral between a and b of f of x, if this is f of x, dx is going to be greater than 0. Okay, so the only way that the area and the only way that this could work, so this integral could be equal to 0 for all a greater than or equal to 0, by the way, is if g of x is equal to 0. Now it might be that, for example, the function is a bit above the x-axis and then a bit below, and it might exactly cancel out. But notice that this is true for all a greater than or equal to 0, not just for some. So even if my function goes like this, and this area above the x-axis is exactly the same size as the area below the x-axis, then, okay, if I integrate between a and c here, or between 0, let's say a is somewhere over here, then yeah, the integral here is going to be equal to 0. Okay, but if a, remember, this should be true for all a. If I choose my a somewhere here now, then this integral is going to be greater than 0. Okay, so for this to be true for all a greater than or equal to 0, the only way that that can happen is if g of x is equal to 0. Now, how would you explain this in your exam? You don't need to be word perfect with this, by the way. You just need to demonstrate that you've kind of got the main idea. that you understand how continuous functions work, and that you understand what the significance of this, that this has to be true for all a greater than or equal to 0. So I'm not going to tell you exactly how to write it. You just have to find a way to articulate your idea. Okay, that's the main thing. This is a very important result in real analysis. When you go to university to do maths, you do real analysis, you will prove this theorem. And you'll do it in a very rigorous way as well. Okay, so then we're still on the same part of this problem, and then it says, let f be a continuous function with f of x greater than or equal to 0. So f of x is greater than or equal to 0 for all x. Show that the integral of between minus a and a of 1 over 1 plus f of x dx is equal to 0 if and only if. So this is a two-way theorem. If and only if. So I might use that symbol, kind of the implies symbol, but with the arrow pointing in both directions. If and only if 1 over 1 plus f of x plus 1 over 1 plus f of minus x minus 1 is equal to 0. Okay, let me just make sure that I've got that right. Oh, for all x greater than or equal to 0. Okay, so when I first looked at this, I had the very usual reaction to this, thinking, I have no idea what to do. Okay, that's fine. The whole point here is that you, rather than just saying, I don't know what to do, and just stopping and just giving up, you take that, you say, okay, I don't know what to do, but I'm going to try some things out. I'm going to try this, I'm going to try that, and I'm going to try the other until I find something that hopefully works, but will at least make some progress. That will at least start taking me in the right direction. Understand that problems on step papers are very, very, very non-routine. They are not types of problems. You shouldn't expect to be going into a step paper and expecting that you're just going to be presented with a load of problems that you just know how to do like that because you've been told the method. That's not how it is. That's not the point of STEP. The point of STEP is that you can be presented with fairly unfamiliar concepts, not necessarily totally unfamiliar, but concepts that maybe don't get so much emphasis on the normal A-level maths and further maths syllabus. And you've got to work with them. You've got to figure out how to work with them. And you can't just sit there and say, well, I've not been told about this, or I've not been told about that. That's the whole point. Okay? You're told what this thing is, potentially. You're maybe given a definition of it. And then you have to determine what some of the properties of that thing are going to be. Okay? So if you feel that you're being presented with new concepts that you haven't really encountered before, yes, that's happening. And that's how it's designed to be. They're not completely, totally unfamiliar concepts to you. It's just you have to make the connection between what you already know and this new thing that you're being presented with. Okay, so the first thing that I tried with this was to, it's quite naively, actually just try and actually carry out this integration in some way. Just compute this integral. So I did the kind of naive thing of just setting u equal to f of x, then you get du by dx equals f primed x. The point was I was going to try to do basically what I'd done in the first part, using integration by substitution. This is not going to go anywhere. I saw very quickly this is going nowhere, because what I'm going to get is the integral of 1 over 1 plus u times 1 over f primed x du and all sorts of stuff in here. This is just, it's not going anywhere because I can't get f primed x in terms of u. F primed x, by the way, we don't know what the type of this function is. We don't know what the form of it. This could be an incredibly complicated function. All we know is, for all intents and purposes, is that f of x is greater than or equal to 0 for all x. That doesn't narrow down the type of f of x into any particular type of function at all. Okay, so this is normal, by the way. That sometimes you'll try things out and you'll look back and you'll think, well, that was silly. That was a bit naive to do that. But the fact of the matter is that you have to generate ideas, and sometimes by doing naive things, you can actually hit on something that's exactly what you need to do. And that's kind of what happened here, actually, because I gave up on that. I thought there's no point in me pursuing that anymore. So then I drew this diagram. Sorry, I think I've made a mistake. That should be a, not 0. Okay, so the diagram that I drew was this: minus a, and I literally just drew a rectangle here. X, Y, 0, and I recognize that the height of this, for this area here to be equal to a, the height of this rectangle would have to be a half. Okay, why was this potentially useful? Well, it took me a couple of minutes to realize why this was going to be useful, but it turns out that it's very obvious, actually. This area can be expressed as the integral from minus a to a of a half dx. Okay, well, the area of this is a, so that means that this integral is equal to a. So guess what? I can replace this integral, this number here, a, with this integral. So in other words, I get the integral from minus a to a of 1 over 1 plus f of x dx is equal to the integral from minus a to a of a half dx. Why is that useful? Well, because I can use the properties of integrals, that if I've got the integral from a to b of f of x plus g of x dx, this is equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. Okay, this is one of the so-called linearity properties of integration. This will be in your, I think this is in the A-level maths formula book. Probably most people will completely ignore this, but this is an extremely useful result in a lot of cases. And if you're ignorant of this, it means that you're kind of limited in some cases. You might not be able to solve this problem if you don't know this linearity property, or if you're not at least familiar with it. So why is this relevant? Because I can write this as this integral minus this is equal to 0. So then this here is effectively my f of x here, and this, the half, is my g of x. Okay, minus, it could be plus minus, by the way. It doesn't make any difference. It's still part of the linearity property. So this is equal to the integral from minus a to a of 1 over 1 plus f of x minus a half dx. And this must be equal to 0. Okay, so I've combined these two integrals because notice that the limits are the same. The limits are the same. Great. So what does that tell us? That tells us that this, because this is a continuous function. By the way, we're told f of x is a continuous function. That's part of the data that we're given. f of x is a continuous function, so therefore, and it's greater than or equal to 0, so therefore there's no problems here with this being equal to 0, the 1 plus f of x or anything like that. So 1 over 1 plus f of x is also going to be a continuous function. So that means that 1 over 1 plus f of x minus a half is also a continuous function. So using this result up here, albeit with slightly different limits, then we can kind of determine that g of x, that this is going to be equal to 0. Now I'm going to bring it more into this form, by the way. I'm not going to just leave it like this, because I don't want to use this result when the limits are actually kind of different here. So I'm going to just modify things a little bit. So I'm going to write this as the integral from 0 to a of 1 over 1 plus f of x minus a half dx plus the integral from minus a to 0 of 1 over 1 plus f of x minus a half dx. Okay, so this is fine. I can use this, but this is a bit of a problem because the limits are the wrong way round, and not only that, one of them is negative. So let's have a look at this here. And I'm trying to be as precise as I can here. I don't want to be wishy-washy with my reasoning. If I'm going to use this result, I want to make sure that I'm using it properly in the right sort of way. Okay, so let's just get rid of this here. So we've got the integral from minus a to 0 of 1 over 1 plus f of x minus half dx. Well, if I make a substitution, t equals minus x, for example, then I get that this is equal to the integral from a to 0 of 1 over 1 plus f of minus t minus a half times dt by dx here would be minus 1. So dx is going to be minus dt. So it's going to be minus dt. So I'm just using effectively integration by substitution. I made my substitution. I'm not actually going to be doing the integration though. So now what I can do is I can flip the limits. Notice that I've got a positive value here now, a and then 0. This seems a little bit strange because normally you'd expect them to be the other way around. You'd expect the lower limit to be a smaller value. That's not always the case, by the way. This is a perfectly acceptable expression. It's just, it looks a little bit weird, but if I want to flip the limits, then I need to use another property of integration, which is the following, that if I've got the integral from a to b of f, this is equal to minus the integral from b to a of f. So I can flip the limits, but it comes at a price, the minus sign. Well, that's what I'm going to do here. I'm going to flip the limits. 0 to a of 1 over 1 plus f of minus t, minus a half dt. But the minus sign will disappear. It'll be minus minus. So it's going to cancel. Okay? So therefore, this integral here I can replace with this one. The integral from 0 to a of 1 over 1 plus f of minus t minus a half dt. Now the t here is what's called a dummy variable. It doesn't make any difference which variable I use, whether I've got t, whether I've got p, whether I've got y, as long as I've got here where I've got the minus t, if I change that to a y, then as long as I change that, this means exactly the same thing. It doesn't matter what that variable is. In particular then, I could actually change this t back to an x. Okay? So, in other words then, now I can use this theorem, or this property that we've already established, on both of these. Okay, you can see. So this to me is important to really get this really, really strictly right. You've got to make sure that the limits are 0 and a here. Okay, if that's the theorem that you've established, and that's the theorem that you're going to use, then you've got to make sure that how you're using it matches with what you're using it on. So, okay, what does that tell us? Get rid of all of this. Kind of running out of space a little bit. Using this theorem, then, it means that 1 over 1 plus f of x minus a half must be equal to 0 for all x greater than or equal to 0. And also 1 over 1 plus f of minus x minus a half is equal to 0, again, for all x greater than or equal to 0. So then it's just adds these two expressions together. The left-hand sides and the right-hand sides. What do we get? 1 over 1 plus f of x minus a half plus 1 over 1 plus f of minus x minus another half, in other words, minus 1, is equal to 0 plus 0 for all x greater than or equal to 0. So that's the starting from this side. By the way, this is remember, it's an if and only if. So what I've done here is I've proved that if this is the case, then this is the case. Okay, and now you've got to prove in the other direction. Okay, so don't forget to do this. Don't forget to do this. However, it's really just, I'm not actually going to write it out. It's effectively just kind of reversing the steps that we've just taken. Actually, am I going to write it out? Yeah, no, sorry. It is basically just reversing the steps that we've just taken. Okay, it might even be argued that what I've done here, the logic is kind of bidirectional anyway. But yeah, okay. Just to save a little bit of time, I'm not going to write the theorem out in the other direction as well. I'm going to jump onto the final part of this part, which is we need to show that this is equal to a if and only if f of x times f of minus x is equal to 1 for all x. And notice it's for all x, not just for all x greater than or equal to 0 here. Okay, so let's have a look. Let me get rid of this then. So it's interesting how such a simple idea, something that you do that you initially might think is of no consequence, actually is the thing that kind of leads you to the solution to the problem. Okay, so ignore all of this other stuff. So we've got this result here. And okay, therefore, we know that 1 over 1 plus f of x plus 1 over 1 plus f of minus x minus 1 is equal to 0 for all x greater than or equal to 0. Therefore, 1 plus, if I multiply through, if I add 1 to each side, and then, okay, I'll write it out in full. 1 over 1 plus f of x plus 1 over 1 plus f of minus x is going to be equal to 1. Multiply through by these two denominators here, so you get 1 plus f of minus x plus 1 plus f of x is equal to the product of 1 plus f of x, 1 plus f of minus x. So we get 2 plus f of minus x plus f of x is equal to, expand out these brackets, 1 plus f of x plus f of minus x plus f of x, f of minus x. Cancel, 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 cancel. This 1 here is going to cancel with, we've got 2 here, so we're just going to end up with 1. 1 equals f of x, f of minus x. This is true for all x greater than or equal to 0. But by symmetry, even if we choose negative values, we're still going to get the same kind of result. So let's say we look at when x equals 4, some positive value, let's say x equals 4, we get that f of 4 times f of minus 4 is equal to 1. But now if we choose x equals minus 4, what would we get? We get f of minus 4 times f of minus 4, which is just 4. So we get the same thing, right? So we could actually extend this from for all x greater than or equal to 0 to just for all x by the symmetry of this expression. Okay, so that establishes the next result. And by the way, these are all if and only if. These kind of so that, if and only if this, if and only if this, if and only if this, and so on and so forth. So we've proved all of the parts now to part 2 of this particular problem. Okay, so let's take a look at part 3 of this problem. So let f be a continuous function such that for all x, f of x is greater than or equal to 0. And f of x times f of minus x is equal to 1. Equals 1. Show that if h is a continuous function with h of x equal to h of minus x, then the integral from minus a to a of h of x over 1 plus f of x dx is equal to the integral from, notice the difference in the limits here, 0 to a of h of x dx. Okay, so there's a few things that you've got to pick up on here. One is that you've been told this. That's going to be important because that means that you can use the result established in part 2. And this means that h is an even function. Okay, so if you've not come across the concept of even function before, this is an even function. An even function is a function that is effectively symmetrical. It has a line of symmetry, a line of reflectional symmetry in the y-axis. Okay, so that's going to be important to us. It's going to be very important. So initially, again, I looked at this and I was thinking, what do I do here? This is a perfectly normal thing to do. Don't expect with step problems that you will just get the answer like that at the click of your fingers. It doesn't work like that. It's perfectly normal, by the way, as well, for you to I can't remember off the top of my head how many problems you're supposed to attempt on a step paper. It's just slipped my mind for a minute. I think it's 6. Don't necessarily expect to answer 6 full problems on a step paper. You probably won't have time to get. If you do, you're doing extremely well, and congratulations. But don't expect that. Don't beat yourself up. If you get 3.5 solutions, then you've done exceptionally well. Anything more than that is just the icing on the cake. Okay, so give yourself the time that you need to think about these problems. Don't expect a solution to just pop out of nowhere, to just come to you straight away. Solutions will pop out of nowhere, sorry. Don't expect solutions to just arrive, to come to you within a couple of seconds or something like that. These are not routine problems. Okay, so I'm just looking at my notes here at what I've done. But one thing that we know then is that because of this condition here, 1 over 1 plus f of x plus 1 over 1 plus f of minus x will be equal to 1 for all x greater than or equal to 0. So that also means that h of x times 1 plus f of x plus 1 over 1 plus, plus h of x plus over 1 plus f of minus x is going to be equal to h of x. So all I've done is just multiply through by h of x. Now here's the little trick, and that's for all x greater than or equal to 0. Here's the little trick. We're going to write this as h of x over 1 plus f of x. We know that h of x is equal to h of minus x over 1 plus f of minus x is equal to h of x. Again, for all x greater than or equal to 0. It does seem that I'm being a little bit repetitive with what I'm writing here. By the way, this is perfectly normal when it comes to writing your solutions to mathematical problems, so that there's no ambiguity about what you mean. Don't be afraid to express your ideas as clearly as you can when it comes to doing mathematics. Okay, so now I can integrate through. And I can also use the properties of the integral to kind of split this apart. So I get the integral from 0 to a of h of x over 1 plus f of x dx plus the integral from 0 to a of h of minus x over 1 plus f of minus x equals the integral from 0 to a of h of x dx. Okay, where a is greater than or equal to 0. Right, so this here, actually the first thing that I did, the first thing that I tried to do here, kind of, again, naively, was, actually I did it at this stage. I tried to write this as 1 over 1 plus f of x over h of x. 1 over 1 plus f of x all over h of x. I didn't know exactly what I expected that to do. I did a similar thing here, but it didn't really amount to anything. I was kind of hoping to reduce it more to the form 1 over 1 plus f of x that we saw earlier, but writing this as 1 over 1 plus f of x over h of x, it's not going to do the job. So again, it's sometimes you try things out and they just don't work. But it's worth trying them anyway, because it's important sometimes for you to see that something doesn't work. Okay, it's just as important for you to become aware of what doesn't work as it is to be aware of what tends to work, what does work. Okay, so this thing here, I'm going to do a similar thing to what I did earlier. Make a substitution, t equals minus x. Okay, so when I do that, this integral will become the integral from 0 to minus a of h of t over 1 plus f of t times, and it's going to be dt by dx is equal to minus 1, so dx is going to be minus dt, so I get the dt and the minus there. And then I'm going to flip the limits again, and I get the integral from minus a to 0 of h of t over 1 plus f of t. This minus sign will cancel, and the t is a dummy variable again, so I can just go back now to x. So in other words, this integral here I can replace with this one. Okay, so this was equal to this is equal to this, so I can replace that with minus a, that with 0, that with x, that with x. Get rid of this now, finished with that. And using the properties of integral, I can combine these two. So another property of integrals is that the integral from a to b of f is equal to the integral from a to c of f plus the integral from c to b of f. Okay, so I'm wanting to go in that direction. All of these properties of integrals, well worth knowing, by the way. Often you won't be told them really, or they won't be emphasized when you do your normal A-level maths. There's something that really, you'll have to figure them out for yourself, or their significance, their importance, you'll kind of have to figure out for yourself. Okay, so I can combine these into the single integral h of x over 1 plus f of x dx equals the integral from 0 to a h of x dx. Let me have a look. Is that what we needed? Yes, it is. That's exactly what we need. Okay, so that establishes the result from part 3. Okay, so let's move on to part 4. Okay, so here we arrive at the final part of this question, which is we need to find the exact value of this integral. So the integral from minus pi by 2 to pi by 2 of e to the power of, let me get it right, e to the power of minus x cos x over, was it cos x? Hyperbolic cosine of x. So it will help for you to be familiar with hyperbolic trigonometric functions, the hyperbolic cosine of x, which is defined to be cos x equals e to the power of x plus e to the power of minus x over 2. That's going to be quite useful. By the way, in this video, I know that there have been a lot of things that I've kind of mentioned, so properties of integrals, certain concepts that you might not necessarily be overly familiar with, and I've not necessarily explained them in full detail in this video. So I'm not going to go into properties of hyperbolic cosine and things like that in this video. That's kind of deliberate in a way. First of all, I don't want the video to just go on forever and ever and ever, but it's also an invitation for you to take on that responsibility yourself of actually finding out about these things. Being a good independent learner, an effective independent learner, is going to be essential if you do plan to go on to do mathematics at university, for example. I'm sure for other subjects as well, economics, computer science, whatever, whichever subjects you do, you'll have to be an effective independent learner. So it would be a good idea for you to get used to that now. If there is anything, by the way, that is unclear from these videos, please get in touch with me. Leave a comment in the comments section. I'll get back to you. If there's anything that you want to know more about. But I reiterate, if you do really want some help with your STEP or your MAT, you want some good preparation for your exams, for your maths exams, please get in touch. I'd love to hear from you. I'd love to be able to help you. It really is a joy to me to help people to get into the university or college or sixth form or whatever it is, or job that they're wanting to do, that they're wanting to go to see people, to help people achieve their true potential, really does bring me great joy. So I'd love to hear from you, and I'd love to discuss your needs and your requirements. So, okay, on with the show. So we need to find the exact value of this. Now, as is typical with STEP problems, there's some kind of continuation throughout the problem. It's not necessarily that every part is related to the previous part, but once you get to the final part of the problem, this is usually bringing certain results together that you've established earlier. Some of them or all of them. Okay, so you're going to have to think very carefully, and sometimes it's very non-obvious how those results need to be used, but you're going to have to think very carefully about how they're going to be used. So I was fairly lucky, I guess, with this, in that my first instinct was to replace this with its definition in terms of exponentials. The thing that really triggered this for me was the fact that I've got e to the minus x up here. E to the minus x and cos x, it's 2 and 2 make 4, right? It's useful to pick up on things like this. So if you didn't know, for example, that cos x is equal to this, you're not going to be able to do this. So if you're doing further maths, you'll come across this. If you're not doing further maths, then you probably won't be doing step 3 anyway. But if you are interested, then these are perfectly accessible functions. You can learn about these if you're just doing normal maths. It's just you're not going to be examined on them. Okay, so what did I do? I wrote this as minus pi by 2 to pi by 2 of e to the minus x cos x over, so it's going to be e to the x plus e to the minus x all over 2, which I'm just going to write up here. Just to save a bit of time. So it's the integral from minus pi by 2 to pi by 2 of, and then I'm going to multiply numerator and denominator by e to the x. Okay, so what does that give me? 2 cos x over e to the 2x plus 1. Or maybe I should write it the other way around, actually. E to the 2x plus 1 is the same as 1 plus e to the 2x. It really doesn't make any difference. Ooh, forgot my dx, didn't I? That's naughty. Okay, so what does this tell me? This tells me that since I know that e to the 2x is greater than or equal to 0 for all x greater than or equal to 0, in fact it's greater than 0, and e to the 2x is continuous, I can even establish results like e to the 2x times e to the minus 2x is equal to 1 for all x greater than or equal to 0. However you want to view it, this function satisfies the conditions that we've been working with really in the previous sections. So if I think about 1 over 1 plus f of x as, in this case, being 1 over 1 plus e to the 2x, and h of x as being equal to 2 cos x. And notice that h of x is equal to h of minus x, because cos x is an even function. Okay, so everything's starting to fall into place now. So, in other words, I've got something here of the form h of x over 1 plus f of x. The integral is from minus a, pen's running out a little bit, from minus a to a dx. It's exactly what I've got, what we were looking at in part 3. Okay, and what we know from part 3 is that this is going to be equal to the integral from 0, remember it's 0 to a, of h of x dx. So in other words, this thing is going to be equal to the integral from 0 to pi by 2 of 2 cos x dx. Okay, let's go back to this pen. Which is equal to, and this is straightforward, right? Integral of 2 cos x, no problem. So it's going to be twice, watch me make a mistake now, twice sine x between 0 and pi by 2, which is just going to be twice sine pi by 2 minus twice sine 0. Twice sine pi by 2 is just 1, so that's going to be 2. Sine 0 is 0, so it's just going to be equal to 2. So the value of this integral, the exact value, is just 2. And it's as simple as that. Okay, so it's making sure that this function here that we're trying to integrate can be brought into a form that is that resembles what we've been working with in the previous parts of this problem. Okay, so that brings us to the end of this. A very nice problem, lots of things to think about, brings in some properties of integrals that you, in many cases, doing the normal A-level maths, you might not have needed to think about explicitly. You might not really have had to think about them very often at all. But for a step paper, completely different thing. You've got to be familiar with these so-called linearity properties. So if there is anything that's been unclear in this video, which I'm sure there's loads of stuff, leave a comment in the comments section or get in touch with me. Just send me an email with your questions and I'll be sure to get back to you. But that's the end of this problem and the end of this video. Thanks for watching.